Good evening, everyone. My name is Aditya Sharma, and this is aircraft propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And we are into 11th week of this aircraft propulsion course. And the theme for today's discussion, the topics for today's discussion are axial turbine, radial turbine, and their examples. So in total, 5 lectures are there. The first 2 lectures have explanations of axial and radial turbine. So we will be discussing these 2 lectures, and then we'll see questions related to these lectures. And instructor for the course is Professor Vinayak Kulkarni from Department of Mechanical Engineering, IIT Guwahati only. And I am also a research scholar here at Department of Mechanical Engineering, IIT Guwahati. So we shall start in another couple of minutes. Let's wait for a few minutes. After that, we can start with the session. Thank you. Okay, so we can start today's session. Okay. So, uh, As I have already mentioned, we'll be discussing turbines today. So before this, we had dedicated 2 weeks, week number 9 and week number 10 on your compressors. So first we discussed centrifugal compressor and then we discussed axial compressor. Okay. The velocity diagrams related to centrifugal compressor and the velocity diagrams related to axial compressor. Then today's content we have is this. So lecture number 34 is on axial turbines. So it's velocity diagrams and the work that is done by this turbine, expression for that, and what is the degree of reaction in axial turbines. Then we shall see questions related to lecture number 34. Okay. Then we shall see topics related to radial turbine. That is lecture number 35. So it's velocity diagrams, HS diagram, stage efficiency, and degree of reaction. So these are the topics, some of the topics related to the radial turbine that have been discussed in lecture number 35. Then there are two lectures where questions related to these two types of turbines have been discussed. Then we shall see questions based on lecture number 35, 36, and 37. All right. So I have a paragraph type of question. So paragraph related to that, few questions are there. Okay. So this is the content of today's session. Then I have given a link here. So this is basically one animation of turbofan engine. So how a flow moves in a turbofan engine, right from its fan, okay, the bypassing of the air and the core engine where you have compressors, then you have your combustion chamber and how from the combustion chamber uh, combustion takes place, right? How the fuel mixes with your air, and then how this gas out of combustion is impinged on your turbines, and then how your turbines rotate, and eventually through the nozzle, this gas comes out in the form of jet. Okay, so I would suggest that you please go through this one animation. Before this, I had given one link in centrifugal compressor of centrifugal compressor also. So that also you can watch. That is in tutorial 9, I believe. Because visualization is very important when we are studying these rotary machine, right? Rotating machines. When we are talking about such machines, it's where it becomes very important that we are able to visualize how the things are happening, how the blades are moving, how the flow is moving. Okay, only then we'll be able to understand the velocity diagrams also and how different velocities are behaving. What is the relative velocity? What is absolute velocity? What is blade velocity? So these things should be very, very clear to us. Right? Then lecture number 24 is there. In lecture number 24, you have first the configuration of your axial turbine. then velocity diagram, then degree of reaction, what is free vortex design, and then constant nozzle angle. So for constant nozzle angle, what condition we need, and for free vortex design, what condition we need. So in our last lecture, we have seen that why do we use free vortex design? So we had assumed that there is a radial equilibrium. Okay. In radial direction, there is no flow. When we talk about our axial flow compressors from the previous week's content. So here we are talking about turbines. But then again, free vortex design, it means same. It is same thing. Okay, then here we have constant nozzle angle. So this nozzle angle is related to your nozzle of your turbine. Okay. So your axial turbine has a nozzle and a rotor. So in configuration, we shall see that. Right. Lecture number 34. This is lecture number 34. Let's see configuration. So if you talk single stage of an axial turbine, so it will have one nozzle, and then it will have one rotor. So this leads to a single stage of axial turbine. So if you go through that video, you'll realize how the nozzle blades are mounted and how these ro rotor blades are mounted in your turbine, right? Then we'll see the velocity diagrams. Okay. The arrangement of blades is somewhat like you have seen in compressor. So you have one shaft and then blades on that shaft along its circumference, right? And the flow then moves in along the shaft, along the axis of the shaft, the flow moves, right? So velocity diagrams I'll draw. So this basically, when we are drawing these, I hope there is no doubt in this that this is just the top view. So if this is the blade, if your blade is something like this, so this top top view we are seeing, okay? The cross section of this blade we are seeing. So your flow will move in this direction. Let's see. So we have this top view we are seeing, right? This is your nozzle blades. Their flow is something like this. This again is the cross sectional view, okay, of your rotor blades. So when we are saying this configuration nozzle and rotor, so this is your nozzle and this is your rotor. Okay. So your nozzle blades will remain stiff and your rotor blades will move. So this is with this direction we have shown this, okay, that this will move. Then this is your relative velocity. Okay, this is your blade velocity. And this is your absolute velocity. This is C2. This is V2. This is U2. Okay? It is like this. This is your axial velocity. So axial velocity component of your C2 in the axial direction. So it will have two components. One will be in the axial direction and one will be in the tangential direction. So your blade also gives tangential velocity to your fluid. And so this is your axial velocity. And this whole becomes your, if you break C2 into two components, two perpendicular components, so this is the speed of blade. Then this is coming in this direction. Because U2 and U3 are same, right? You can call it U only. And then there are fluid angles and blade angle. So with C, you have fluid angle. With your relative velocity, you have blade angle. With your relative velocity, you have your blade angle. With your absolute velocity, you have your fluid angle. Okay. Then, so this is your velocity diagrams for your axial flow turbine, right? Then in combined form also we can write in combined form. Velocity diagrams can be written in this way. Because your u is same, right? The blade velocity is same. So we can just write it this way.
This is your blade velocity. I hope it's clear. What is the blade velocity related to your rotor blades, right? The nozzle blades are stiff, they are not moving. So here we are talking about which blades? Blades of your rotor. And these are fluid angles and blade angles.
Right? Just give me a second.
So in combined form, we have this. So I was talking about these angles, blade angle and your fluid angle, right? So related to your when your fluid exits your rotor, so this is your alpha is for your fluid angle and beta is for your blade angle. Okay. So this is about the velocity diagram. Then tangential velocities also we can write. So for C3 we can split this. So because these are so there are two directions involved here. Radially, we assume that there is equilibrium from your free vortex design. This is CA3. Here, this is A2. Okay. Then this is your C. This is for local W, CW3. And then if you split this, if you split, this is CW2. Right? So we have these tangential velocities. So two velocities, one is tangential and one is your axial velocity in your axial flow. Then from here, what we will see from velocity diagrams only. So first is that your axial velocities, we assume that they remain same, right? So we say CA2 is equal to CA3 is equal to C. Okay. Right? Then from trigonometry, right? And this, what we can attain is this. This relation we can attain, right? This relation you will see in lecture number 34. This has been
explained to us, right?
And from this, you can get this tan alpha 2 plus tan alpha 3 is equal to tan beta 2 plus tan beta 3.
So we are analyzing your our flow across the rotor of the axial turbine, right? So then if you talk about work done, you can write as mass flow rate, then CW2 U2 minus CW3 U3. At the exit, you'll have more energy, and that then will be imparted to your this turbine through your fluid, right? So that's why this term will be higher than this term. Okay. The first term will be higher than the second term. Okay. And here, because your blade velocity remains same, so in that case, W2 is equal to this. Then there is expression for change in total temperature of the whole stage. But then I believe, yes, I should skip that, right? You can have a look of this expression or formula for this from lecture number 34. Yes. Then I can just write for degree of reaction. So what is degree of reaction? Degree of reaction basically is the enthalpy change in your rotor, then the enthalpy change across the whole stage, the nozzle and your rotor, both. So what is enthalpy change in your rotor? Then the enthalpy change in your whole single stage. So that is your degree of reaction. So there is expression for it. So I can write that. So this is half of CA by U tan beta 3 minus tan beta 2. So this is the expression. Right. Then if your degree of reaction is half, that is the half enthalpy change is taking place in your nozzle and half enthalpy change is taking place in your rotor. In that case, so this has been again discussed in the lecture. So in that case, your beta 2 will be equal to alpha 3 and your alpha 2 will be equal to beta 3. Okay. Then there is blade loading coefficient. This is psi. Blade loading coefficient basically is with respect to the blade energy that we have in this turbine, right? Related to your this rotor related to your velocity of your rotor blade. So with respect to this, how much work we are getting? Okay. So this is expression for this is
tan beta theta. Then we have a TS diagram, temperature entropy diagram. So what will happen to your temperature and what will happen to your entropy across the nozzle and your rotor? So it goes like this. We'll start from here. So we have one. Okay. So the numbering of these pages we can give. So this is one. Okay. When the fluid enters the nozzle. Then second, when the fluid enters the rotor. Third is when fluid exits the rotor. So this is here. Okay. So this is the static part. This is nozzle. What is happening? Your static temperature is decreasing, right? So your straight line, if you draw, you'll get total temperature and corresponding to that, you have your pressure, total pressure. Right? Then this is related to your nozzle. Then further there is expansion. Okay, so this is your three, and then static pressure related to it. Total pressure related to it. Not three. This is your nozzle. This is your rotor. Okay. So this is the TS diagram for your axial flow turbine. Then there are two conditions. One is your free vortex condition for your free vortex design, which is from previous only. Tangential velocity into your radial distance should be constant. Okay. Then for your constant nozzle angle, this condition is there, which is 2 r sine square alpha 2 is equal to constant. Okay. So alpha 2 is this angle. Alpha 2 is this angle. Right. So when this is entering the rotor, so this remains constant, or because axial flow is directly proportional to your tangential flow. So in that case, right? So this is for your constant nozzle angle. You need this. I hope this is understood, right? So you have your nozzle, and then you want that the axial flow and then this radial distance, right? And then this alpha 2 is there, right? So for different R's, radial directions, so this has to be whole, this left hand side has to be constant for a constant nozzle angle. Then let's see, this is about lecture number 34. Then let's see the questions related to. First question is blade loading coefficient of an axial flow turbine is. The four options are there. With respect to the energy that we are giving, okay, in terms of your blade velocity, right, in your compressors. And then we have to compare this blade loading coefficient for your axial flow turbine with your axial flow compressor. So if we compare these two values, so what we can comment on that? First option is your this psi is higher for your axial flow compressors, higher than your axial flow compressors, which is, and the second one is it is lower than your axial flow compressors. And the third is same as an axial flow compressor. Fourth is we cannot comment or none of the above. Or I could have written we cannot comment. So which one is the correct option? So out of these four options, A option is the correct one here. Okay. Your blade loading coefficient for your axial flow turbines is higher in case of your turbines when you compare with your compressors, right? Axial flow compressors. One basic difference you always have to keep in mind that in your compressors you are giving work, right? And then in your turbines you're getting energy of work, right? Then
Second question is, in case of an axial flow turbine, the rotor blade passage acts as a, so your rotor blade passage acts as a nozzle or diffuser. So in case of your axial flow turbine, your rotor blade passage acts as a nozzle. Okay. Then third question is, in an axial flow turbine rotor, the relative velocity component dash from inlet to outlet. Relative velocity component, what happens to your relative velocity component? Whether it decreases, increases, what happens? So V is your relative velocity component. So if we see the diagram, so your relative velocity component increases. It increases from inlet to outlet. Okay. Then fourth question is there. So let's see question number 4. So it says that in the rotor of an axial flow turbine, which of the following components of velocity decrease? From inlet to outlet. So whether this is absolute velocity, whether this is tangential velocity, whether this is both absolute and tangential velocity, whether this is relative velocity. So as I've already said that in your turbines, you take energy from the fluid, right? And in your compressors, we give energy to your compressor, and which it in turn gives it to the fluid, right? And opposite is in your turbines. So what will happen?
both of your absolute velocity and your tangential velocity, they decrease. So tangential velocity you can see from CW2 and CW3. Okay, so CW3 is less than CW2. Also, your C3 is less than C2. So is the right answer to this question. So this was question number 4. So is the right answer to this question. Then we have lecture number 35. Lecture number 35, you have radial turbines that have been discussed. Then in the starting, schematic has been discussed. Okay. So for schematic, you can refer to lecture number 35. Link I'll give in the description of the original lecture of Professor Vinayak Kulkarni. And then velocity diagrams I'll draw. Okay, and we can discuss these velocity diagrams. Then stage efficiency also has been discussed, and degree of reaction. So expressions for these two I can write, and then velocity diagrams I can discuss. So lecture number 35. So please remember, in your axial turbines, the velocities involved were in axial direction and tangential direction. Okay. And the velocity diagrams
also discuss tangential and axial direction. Okay. And then in your radial turbines, the velocities involve velocities involved are velocities, two directions, radial direction, and the second one is tangential direction. Okay. Or what we call also as work. Okay. Then first we'll see. So your your radial turbine has a nozzle ring, then it has impeller, then it has a diffuser. For this, you can have TS diagram. And the TS diagram looks somewhat like this. Because it's a turbine, obviously the expansion will take place. Okay, but then how exactly? So let's see this. So across the nozzle ring, first of all, we have this form. Okay. Then across the impeller, we have this. This is for your diffuser. So it's fun. One is this. This is two.
So this is from 1 to 2, you have your nozzle ring. 2 to 3, you have your impeller. So you had impeller we had impeller in our centrifugal compressors also, right? Then this is your diffuser, 3 to 4. This is 4 basically. Okay, and this is P not 4. This is P3. So this is your P not 3. Total pressure for your third state of fluid. This is for your P not 1. Okay. Yes, this is for your second. Second one. This is P not 2. This is your diffuser. Nozzle ring, impeller, and diffuser. Yes. So across the nozzle ring, how the temperature behaves or how the enthalpy behaves, and across the impeller, how your enthalpy behaves, enthalpy of your fluid, and across the diffuser, what happens. So this is it. ES diagram for your radial flow turbines. Okay, then velocity diagrams are there. But before drawing the velocity diagrams, we'll just take a short 5 minutes break. Okay, because it's already 7. 1 hour since we have started our session. So we'll take a short break and then we'll come and continue with this remaining session. Thank you.
Okay, so let's see the velocity diagrams for our radial flow turbine. Okay. So first is this. So 2 to 3 is your impeller. Okay. Third is this section. Third is this section. So this is V2, this is C2, and this is U2. This is alpha 2. This is beta 2. But let's see. This is beta 2. Then uh, this, then this. This is relative. This is absolute. And this is blade. If you have the component of your absolute, you have this as tangential. Okay. And here this is tangential. PW2. So two velocities are involved. One is your tangential and one is the radial. So I have already mentioned this. PR3. Here this is PR2. Okay. All right. Then, so this is your velocity diagram. Now, if you want your inward flow, 90-degree inward flow radial, right? So for that, your blade angle has to be 90-degree. Okay. At the entry, right? And then at the exit, you have your fluid angle equals to 90 degree. So if you see your lecture number 35,
So from there only. So this is your alpha 3 and this is your beta 3. Okay. Now for 90-degree inward flow radially, the inlet will look like this. Okay. So inlet is this basically. So it will look like this. This is alpha 2. This is beta 2 equals to 90-degree. This is C2, V2 equals to CR2. This is U2 equals to CW2 at inlet. Okay. And then at outlet, you have this is like this. Alpha 3 is equal to 90-degree. You have beta 3. You have C3. C3 is equal to CR3. Then V3 you have. Okay. So this exit will only be in radial direction. There is no tangential component here, right? And then you have this blade velocity U3. Okay. Yes. So if you talk about work done by this turbine, right? Work done. So WT will be equal to, this is radial flow turbine. This is U2 CW2 minus U3 CW3. Then for 90-degree IFR, PW3, PW3 is equal to 0. We have seen this. Okay. Only in radial direction flow is there. Then implies W2 is equal to U2 CW2. Okay. And CW2 is because equal to U2. So it becomes U2 square. All right. So this is your radial flow turbine. Then there is expression for stage efficiency, which basically is stage efficiency, which basically is ideally what work would we have, we would have extracted from the turbine, and in reality what we have. So this is WT by WT dash. So this one is your real one, and this one is your ideal one. Okay. WT is loading coefficient with loading coefficient, this, and then WT dash is your enthalpy change. This. So from here we can get stage efficiency, and then your degree of reaction is the expression I will just write down. This has been derived. So this is your expression for your degree of reaction. Okay. Then moving on to questions. So this is about your radial flow turbines. The two velocities are important here. One is your radial velocity and one is your tangential velocity. Second one is your tangential velocity. In your axial flow turbines, again, two velocities. One is your tangential velocity and one is your axial velocity. Okay. Yes. So tangential velocity is important for both both the type of turbines. But then for your axial turbine, other than tangential, axial velocity of the flow is important, and in your radial turbine, radial component of the velocity is important. Okay. Then there are numericals in lecture number 36 and 37. Okay, so this link I'll give in the description. You can go through these lectures with examples of these two types of turbines. So I have one few numericals also on axial turbine, so we can discuss them. So question number 5, let's see. This is in an impeller of inward radial flow turbine, the absolute velocity dash from inlet to outlet. So what happens to your absolute velocity? So what happens to your absolute velocity? So this is absolute velocity. So absolute velocity, what happens? So absolute velocity decreases. Okay. C2 and C3, if you see, so absolute velocity decreases. Then question number 6, it says that in radial flow turbine, the stagnation temperature of flow passing through the exhaust diffuser. So stagnation temperature, what happens to the stagnation temperature when we move across the diffuser? So let's see the TS diagram here. So if you move across the diffuser from the exit of impeller, you are entering the diffuser. Okay, so this is 3 to 4. If you see 3 to 4, what happens to your stagnation temperature? So stagnation temperature remains constant. Okay.
So you can see this stagnation temperature, this one. So stagnation temperature is remaining constant. That is T03 is equal to T04. Okay. So it remains constant. Okay. That's question number 6. Then moving on to question number 7. For a radial flow turbine, which of the following options is correct expression of degree of reaction? So enthalpy drop in impeller to total enthalpy drop. So this is right. Okay. The enthalpy drop in your impeller. So enthalpy is dropping in your nozzle ring also. But then in with respect to the total enthalpy drop in the stage, the enthalpy drop in impeller. So this is degree of reaction. So degree of reaction is also the kinetic energy change of the blade velocity. Okay. And kinetic energy change of the relative velocity. Okay. So this is with respect to your total work done, right? Right. So kinetic energy just from blade velocity we put, right? Right. But I hope you understand this, right? And then if you see work done minus kinetic energy change of absolute velocity. So this is again correct one, right? So with respect to your total work done by the whole turbine, the work done minus the kinetic energy change of your absolute velocity. So A, B, and C, all the options are correct in that case, right? A1 is correct. And then in terms of your velocity, also you define the degree of reaction in terms of velocity changes across your impeller and then across your stage, right? So all the options are correct. In that case, B is the correct answer to this question. Then let's see this. So I've forgotten to change the values here. So this is 870 and this is 22. This is 1.4. This is 17. This is 0.87. This is 56 degrees. Okay. So this is basically the question we have. So the following data is given for a single stage axial turbine with free vortex condition. That is CW into R is constant. Then total head inlet pressure is given. Total, that is P01 is given. Then T01 is given. Then mass flow rate is given. Static head pressure at mean radius is given. Okay. Right. So this is given.
that is 1.4 bar. Then what is given to us? Mean blade diameter to height. So d by h is given. Nozzle efficiency is given. Nj is given. Nozzle outlet angle is given 56 degrees. And then Cp for gas and gamma for gas is given as percentage. So question number 8 to 12. Not one is 5.9 bar. Then T not one is 870 Kelvin. It's 22 kg per second. Then static at mean radius. One point four bar. What else? D by H is given as 17. Or your nozzle efficiency is given as this. Nozzle outlet angle is given as 56 degrees. Then Cp is given as 1.147 kilojoule per kg Kelvin. And gamma is given as 1.33. So this all has been given. Okay, then let's see the questions. So this is your turbine. So nozzle area at the exit has been asked. So we need axial velocity, right? We need axial velocity, mass flow rate we have. Rho2 also we can calculate. Okay. So question number 8 is there. So please keep this in mind that this from here we have to calculate this. A2 is equal to mass flow rate by rho2 CA2. Now we need to calculate CA2 rho2. Okay, so that we shall see gradually. So we'll start with here that your first efficiency is given as this. Okay. And then isentropic relation is given as this. Right. From here, T2 dash we can calculate. Right. Now placing the values, T naught one is given to us 870, and P naught one also is given to us 1.4. Sorry. This is P dash not one. So P2 dash is 1.4 and P naught one is 5.9. Okay. Gamma is this and this is this. If we calculate this, this will come out to be 608.85 Kelvin. This is this. Okay. Then placing values in NJ implies 0. Nozzle efficiency is this. P naught one is 870 minus T2. 870 minus 608.85 implies T2 is equal to 870 minus 0.87 into 870 minus 608.85. This. If you calculate this, this will come out to be 642.75 Kelvin. So this is your T2. Now, why we have calculated T2? Because this will be used in your rho 2 calculation. Okay. Just save your T2 for later use. Then is your CA2. We need to find CA2, right? For CA2, what you will do is you will find C2. Absolute velocity will find, and from there we can get uh, axial velocity. Okay. If you see this. So for H naught one is H2 plus C2 square by 2, right? Then your C2 is 2 H0 1 minus H2 root. Okay. And this is 2 CP T0 1 minus T2 root. So this is 1147. This is 870 and this is 642.79. So your T2 has been used here also. Okay. So this becomes 721.95 meter per second, right? Then if you see, let's say this is C2, okay, and this is alpha 2. This is axial, this is tangential components. So from here, what we have, CA2 by C2 is cos alpha 2, implies CA2 is equal to C2 cos alpha 2. This we have. So hence here CA2 is equal to 721.95 into cos of alpha 2, that is 56 degree. Nozzle outlet angle, okay, which is alpha 2 is equal to 56 degree. If we calculate this, this will come out to be 403.70 meter per second. Okay. Then we have CA2, we have. Now you see rho 2 is equal to P2 R T2. Okay. Now R we can calculate from where? Cp gamma minus 1 by gamma is your R into T2. Okay. Or P2 into gamma by Cp gamma minus 1 into T2. So this is your rho 2. So then coming back to, so A2 is equal to, coming back to this first expression. So this A2 is mass flow rate by rho 2 CA2. Then mass flow rate Pp to gamma minus 1 P2 by P2 gamma CA2. So this we are giving here. Okay. And then now if you place values, 22 into 1147, 0.33 into 642.79 divided by P2 is 1.4 into 10 is power 5, then 1.33 into 403.70 CA2. If we calculate this, this will come out to 0.07 meters. So this is question number 8. This is question number 8, right? Then question number 9. Mean blade diameter of rotor blade is. Mean blade diameter we need to find out. Now Question number 9 solution. A2 is pi dmh. This is your A2. Okay. Or 2 pi RH. And implies 0.07 is equal to pi dm by 17. Okay. Because dm by h is 17. So dm by 17 is equal to h. Implies 0.07 is equal to pi dm square by 17. Implies dm is equal to 17 into 0.07 divided by pi root. So if we calculate this, this will come out to be 0.6154 meter. So this will come out to be this. Okay, so this is your mean blade diameter. Which is also 61.54 centimeter. Then from here, h is dm by 17, which is 61.54 by 17, which is 3.62 centimeter. So this is h. But in question, we have been asked this. So this is your mean blade diameter. Then radius at the root and tip of the rotor are. At the tip and at the root, what the radiuses are. So this is this question number, this is, I believe, 10. This is question number 10 solution. The radius at root is equal to r mean minus h by 2. So this is 30.77 minus 3.62 by 2. So this is 30.77 minus 1.81. So this will come out to be, so this is in centimeters of it. So from here, Rm is equal to 61.54 divided by 2, that is equal to 30.77 centimeter. So 30.77 minus this. So this will come out to be 28.96 centimeters. That is 0.2896 meters. And R tip is equal to R mean plus h by 2. So this is equal to 30.77 plus 3.62 divided by 2, which is 30.77 plus 1.81. So this is equal to 32.58 centimeter, that is 0.3258 meters.
So this is there. So radius is this and this, root and tip. So then if you see the results here, so these results are there. 0.22. Then you have question number 11. Which asks for absolute velocity angles at the root of the rotor inlet. So absolute velocity angle basically is alpha. Okay. Alpha we will calculate. So now for root. Now you see for your mean, the alpha 2 is given 56 degrees, right? But then at the root, if you see, alpha 2 will be different. Okay. So your vortex, free vortex condition, using free vortex condition, you need to find this. Okay. What will be your alpha 2? Or fluid angle, sometimes we say. So we need to calculate alpha 2 at root. Okay. So for this, what you will do is, because it is like this, so this is V2, this is alpha 2, implies alpha 2 is tan inverse of PW2 by CA2 of root. Okay. Yes. Right. So now we need to calculate CW2 at root and CA2 at root. So that we can do from your free vortex condition. So using free free vortex condition. What do we have? P WR is equal to constant. Implies PWR for your mean position, CWR for your root, PWR for your tip is same. Okay. Then first we will calculate CW2 for mean position. If you again see the diagram, you can figure out that if you want to calculate CW2, so you can do it this way.
Then C2 we already have calculated from previous questions. For mean position, your alpha 2 is this. So if we calculate this, this will come out to be 598.52 meters per second. So this is CW2 mean. Then for CW2 root, we will use this. CW2 root, CW2 into R of root is equal to CW2 into R of mean. Okay, implies CW2 of root is equal to CW2 R of mean by R of root. So this is 598.52 we have just calculated, and your mean radius is 0.3077 meters, right? And then this is 0.2896 is your root radius. And if we calculate this, this will come out to be this. This is this BW2. Then similarly, CW2 is equal to CW2 into R of mean by R of tip. This will come out as okay. So first we calculate this. So this will calculate later. Or if this has been asked somewhere, CW2, if this has been asked. So we'll calculate this also. But for that, let's calculate alpha 2 for root. Alpha 2 for root is, hence alpha 2 for root is tan inverse of W2 by CA2 root. So this will come out to be tan inverse of 635.92 by 403.70. So this will come out to be this. Then now CW tip. Here we can write similarly. W2 into R by R tip. So this is 598.52 into 0.3077. So this will come out to be this. And then implies alpha 2 tip is equal to tan inverse of CW2 by CA2 tip. This will come out to be 54.46 degrees. So this is then absolute velocity angle at the tip. So at the tip it is 54.46. At the root it is 57.59, and at the mean position it is 56 degrees. Okay, so this is how the alpha 2 is changing as per the free vortex condition. At the root it is 57.59 degrees. Then last question is static temperature at the root and tip of the rotor inlet R. So for static temperatures, you see is equal to E naught minus E2 square by 2Cp. So here E naught 2 we have, okay. Then so this is yes across the nozzle your total temperature remains same. So T naught 1 and T naught 2 both are same thing, right? Either you write T naught 1 or you write T naught 2. So this now T naught 2 we have 870. Then C2 we need to find out. CP we have, and then T2 we need to calculate. So C2 we need to calculate. So C2 for root is equal to CA2 by cos alpha 2. From C omega 2 also we could have calculated. But if remember the same thing, C2, this comes out to be 403.70 divided by cos of 57.59 degrees. So if you calculate this, this will come out to be 753.20 meter per second. Okay. Then C2 tip, if you see, this will come out to be CA2 by cos alpha 2 of tip. So this is cos of 54.46 degrees. So this will come out to be so this will come out to be 694.51 meters per second. Then hence T2 root is equal to E naught 2 minus E2 square of root divided by 2Cp. So this is 870 minus 753.20 square divided by 2 into 1147. If you calculate this, this will come out to be 622.69 Kelvin. Then T2 tip, if you see, this is T naught 2 minus C2 square tip divided by 2 CP. So this will come out to be 870. 694.51. 659.73 Kelvin. So this comes out to be this 622 and 659. So at the root, the static temperature will be lower in comparison to static temperature at your tip. So at your tip, your static temperature will be high. And the fluid angle is low at your tip in comparison to it. So this is it about today's session. We have come to the end of this session and I'll just conclude this session. So this session was on turbines used in jet engines or gas turbine engines or aircraft engines. So two types of turbines basically are. One is your axial turbine and second one is your radial turbine. So first we considered axial turbines where you have a nozzle and a rotor, okay, which makes a single stage of a axial turbine. Then we saw questions related to this axial turbine, its velocity diagrams. So in axial turbine, uh, the velocities of fluid in axial direction and tangential direction are of importance to us as far as the analysis of the fluid in the turbine is concerned. And then we moved on to radial turbines, where then again the velocities concerned are tangential velocity and then is radial velocity. Then we saw expressions for stage efficiency, work done, and degree of reaction. So we saw expression for degree of reaction and axial turbine also. Then we moved on to a few questions related to your radial turbines. And after that, we saw one numerical, one paragraph type numerical. So in this paragraph based questions, we had 5 questions based on this paragraph. So this was on axial turbines with free vortex condition. Okay. So this is it about today's session on turbines, and this was week 11 of this course. And next session will be the last week of this course. As far as the content of this course is concerned, so this is a 12-week course. So uh, in terms of the content of the course, the last session is on coming Tuesday, but then we have scheduled one more session on 16th with same timing 6 to 8 p.m. So next session will be on 14th related to week number 12 of this course, and then we have another session on week on 16th of this month. So that will be a course concluding session. So there we will just quickly in March will quickly revise all the topics that have been covered so that we can have a quick recap of the whole course. Okay. So till then, goodbye and thanks for watching this session. Next session will be on coming Tuesday, the same time, 6 to 8 p.m. Thank you.